Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. We've just established the fundamental formula of the Algebraic Calculus, which is this one right up here. It's a formula for the signed area of a segment of a particular polynomially parametrized curve, a relatively simple one of the form alpha to the m, alpha to the n. And the formula was that this signed area from 0 to 1, essentially the simplest signed area, is given by this nice fraction n minus m divided by 2 times n plus m. So the difference between the exponents divided by 2 times the sum. Okay, we are going to be moving towards the fundamental theorem of algebraic calculus, which is really an enlargement of this formula. This formula sits at the heart of it, but it's a sort of a bigger picture. But before we do that, I think it's a good idea for us to touch base with more familiar traditional calculus, and I want to show you how this formula really meshes with standard theory, even though it's perhaps novel looking. So we're going to do that by looking at an example. Okay, very specific example. We're going to look at the particular curve, gamma, which is alpha cubed, alpha to the fifth. And it's a curve that looks something like this. So m equals 3 and n equals 5. And according to the formula then, the signed area of this thing, which is this area that we have here, from 0 to 1, and there's a straight line coming back. So that signed area there, positively oriented, is 5 minus 3 divided by 2 times 5 plus 3. So that's 2 over 2 times 8, so a total of 1 over 8. That's that signed area. Now, this curve is not really a function. It's an algebraic curve. If we want to write it as an algebraic curve, its equation would be x to the fifth equals y cubed. You raise this to the fifth power, that's equal to what you get when you raise this to the third power. We're not going to write it this way. This is what you would do in a traditional calculus course. You would divide the exponents here and you would say y equals x to the 5 over 3. And you would think about this as being a function that inputs a value x and outputs a value y. We're not thinking about that way at all. That's, to us, a misrepresentation of arithmetic because you can't actually perform this operation. This is a fake operation at the level of actual real numbers. And in order to sustain this fake arithmetic, you need this fake theory of real numbers. So the whole thing is just, quite absurd, really, from a logical point of view. We're going to stay clear from that. It's all algebraic, and we can get at the signed area purely algebraically, and here it is. It's a beautiful thing. There's no irrationalities at all in this picture. Okay, I want to emphasize that. This is a completely rational picture. In fact, some later course, I'll show you how this kind of formula actually extends to finite fields too, which is very nice. Okay, so I want to have a good look at this, but from a sort of limiting point of view. So we're going to look at some limits and how we might make that coincide with what's going on here. Now, most of you will know that I'm not a fan of the traditional theory of limits because it involves things that we cannot do, so we end up just talking instead of being able to compute. But nevertheless, classical integral calculus relies very heavily on these limits, both to define and to compute, so-called compute, areas or integrals. And it's highly dubious for at least a couple of reasons. One of them is that the notion that everything starts with, the notion of the limit introduced in the context of the limit of a function as x approaches a equals something. This involves infinitely many checks to verify. It's actually a very subtle concept. And students are convinced that they can understand this because they're given lots of little baby examples in which they can work things out. So sort of like a theory that's like this big, and we're only verifying it for some small little corner like this, and after we've done that enough number of times, then we say, aha, we understand the theory. The actual real definition involves an infinite number of checks, so it's something that you can't actually do really. And the other major problem with this whole approach is that when you actually get to what you really want to do, which is to define an integral, like an area under a curve, you have some formula like this. So this is a traditional calculus formula, something like this. The integral from a to b of f of x dx, and there's some limit where you're limiting over a partition. So you partition the interval a, b, and then you let this partition size go to 0, and for each partition you're forming some sum, kind of a Riemann sum of lengths times approximate widths and so on. And unfortunately, the limit that's occurring here, this structure here, is quite different from the limit that one spends time actually studying. So this is a kind of a baby situation compared to this one. There's no real theory of this typically that's derived, but nevertheless students are just supposed to intuit proper understanding of this from having done this baby exercise previously. So all of this, in my view, is highly fraught logically, and that's why traditional calculus courses just sort of wave over it very quickly, and students are told that later on they will understand this more thoroughly, and then later on they're assumed to have already incorporated this from their earlier days. So it's all quite unfortunate, really. But this is the story, the usual story. So even though we don't believe in this version of limits, nevertheless, the fundamental idea of a limit is still a useful one. The idea that as something approaches a value, something else can approach a different value. So there's a kind of a limiting aspect. This thing here is moving towards this. This thing here has a limiting value of something else. Okay, so we can still interpret things like this, and we can try to then take some simplified version of this and connect it with our fundamental formula. All right, so we're going to look at our example from a spline point of view and then think about what happens in the limit as the size of the spline gets bigger. So here's our strategy. We're going to approximate the curve that we're interested in, the curve gamma, by a spline, a0, a1, a2, up to an. Okay? And the kth point in this spline is going to be given by gamma at k over n. So we're going to be running from 0 to 1, and we're basically dividing this up into n equal pieces. So there's 0 over n, and then there's 1 over n, 2 over n, 3 over n, all the way up to n over n, which is 1. And the kth one is k over n. And so the value of the curve at k over n is k over n cubed, comma, k over n to the fifth. Right, so that's a point on the curve, and that's the kth element in our spline. Okay, so let's look at the signed area of this spline. So here's the spline, goes from here to here to here, all the way up to here to here. And we're taking the signed area of this thing, so it's really the area of this polygonal spline coming all the way back there. Okay, we know how to calculate the signed area of such a spline. It's the sum of the signed areas of each of its little pieces. So it's a sum from k equals 1 to n of the signed area of a sub k minus 1, a sub k. Okay, so what's a signed area of an individual piece like this? Well, there's always a factor of a half, so let's pull that factor of half out. And then what we have to do is we have to take a cross product between essentially the k minus first point and the kth point. Okay, so the k minus first point is just like this one, except that there's k minus 1s here instead of k's. So we're going to take the first term in the k minus 1 term, which is k minus 1 over n cubed, and multiply it by the k term in the second one, k over n to the fifth. And then we're going to subtract the k minus 1 over n to the fifth times the k over n cubed. It's taking the cross product of those two adjacent spline vectors. Okay, and we look at this thing, and we put, first of all, brackets around it so we don't get confused about the sum. And now we want to simplify things. Well, there's a factor here of n cubed and n to the fifth in both of these. So there's a total of n to the 8 which can come out into the denominator out front. What does that leave us with? Well, there will be a k minus 1 cubed and the k cubed as a common factor of both of these terms in the numerator. So let's factor those out. K minus 1 cubed, k cubed. What will be left will be a k squared from this term and a k minus 1 squared from this term. So things simplify a little bit to this. And of course now this can be further simplified to, well, the difference here will just be 2k minus 1. The k squareds will cancel and we'll have 2k minus 1. Okay, so before we go on, I just want to point out the significance of two of the numbers here. So first of all, this 8 that's appearing. Okay, that 8 is really the sum of 3 and 5. Okay, because there was an n cubed here and n to the 5th, so that was the total of 8. That 8 is happening because it's the sum of 3 and 5. And the other number that I want you to keep in mind of is the coefficient of k here, the 2k. Okay, that 2 is happening, well, it's because we've pulled out the common factor of 3, and then what's left over is the difference. So 5 minus 3 that's responsible for there being a 2 there, and for then there being a factor of 2 when we expand this out. Okay, so we'll keep that in mind. So we're going to simplify this, and then we're going to see if we can deal with this sum somehow. Okay, so far we've got this spline. We're taking its signed area. We've computed that it can be written as 1 over 2 times n to the 8 times the sum from k equals 1 to n of this expression involving k minus 1 cubed, k cubed, and 2k minus 1. All right, so let's expand this thing out. We expand it out, we get a little polynomial in k cubed minus 5k to the 4th plus 9k to the 5th minus 7k to the 6th plus 2k to the 7. And I want to point out that that 2 there is that number that we've already pointed out. That's the difference between the n and the m that's appearing there. And there's still the 1 over 2 times n to the 8 out front. Okay, so how are we going to compute such a thing? Well, we have sums of powers of natural numbers going from 1 to n. Well, that's exactly a Faulhaber kind of situation, right? That's a Faulhaber polynomial there. It's exactly what we've spent time learning about. So we know how to compute these things. We need the Faulhaber polynomials. If we sum k cubed from k equals 1 to n, it's the third Faulhaber polynomial evaluated at n. And similarly, we're going to get minus 5 times the fourth one evaluated at n, plus n times the fifth one, minus 7 times the sixth one, plus 2 times the seventh one, all of them evaluated at n. And then we're going to divide by 2 times n to the 8. And I'm just reminding you here, the jth Faulhaber polynomial s sub j of n is the sum of the jth powers, the natural numbers from 1 up to n. And that's how it looks like in summation notation, with k as an index here. Okay, so our strategy is going to be that we're going to calculate this thing because we know how to obtain Faulhaber polynomials, so we can write out explicitly what this thing is going to be. And then we're going to be interested in this whole expression after we've divided by the n to the 8 to see what happens to this thing as n gets large. N is the number of points in our spline. If n increases, that means the spline is getting finer and finer. It's a better and better approximation to the curve. And so we would expect that the area of the spline is getting closer and closer to the area of the curve, at least if we have a reasonable notion of area of the curve. This will be a test to see whether our formula is a reasonable one or not. Okay, so we have some Faulhaber work to do here. So I could just list the Faulhaber polynomials and then take that linear combination that we need. But I want to remind you about how to get the Faulhaber polynomials in case you're on a desert island and you need to do this kind of calculation. So the method that I suggested to you, the sort of fast and efficient way, assuming you have some linear algebra computational device ready, is to form this Pascal-like matrix with almost the rows of the Pascal triangle, but not quite, with the sort of leading ones removed. And then we have sort of alternating diagonals of plus and minus and plus and minus and so on. And we're going to go down to the 8th row there. Okay, so we take that matrix, and it's an 8 by 8 matrix, and we take its inverse. Okay, taking its inverse, we get this matrix here. And this matrix, happily, contains all of the Faulhaber polynomials from the 0th one down to the 7th one. And the way to interpret these things, so each one of these corresponds to a Faulhaber polynomial, and these sort of columns correspond to powers of n, starting with n, n squared, n cubed, n to the fourth, n to the fifth, n to the sixth, n to the seventh, and n to the eighth. So for example, the seventh one would be 0n plus 1/12 n squared plus or minus 7 over 24 n to the fourth plus 7 over 12 n to the sixth plus 1/2 n to the 7 plus 1/8 of n to the eighth. And I want to point out that while a lot of this table is a little bit unpredictable, especially this first column, there's the Bernoulli numbers there, it's a bit unpredictable. But the further to the right you go, the more amenable to understanding these numbers are. And by the time you've gotten to the diagonal, everything is very simple. It's just the reciprocals of the natural numbers along there. And I also point out that the one right to the left of that other diagonal is also very simple, just halves. Okay. So what's a fast way then of getting the actual thing that we want? So we want a certain linear combination of the Faulhaber polynomials. And the coefficients are given by this. So this is 1 times S3, so we have to take 1 times this one and minus 5 times this one and so on. So the fast way of doing this is to multiply this matrix, take this matrix, call it Q inverse. That's consistent with the notation I think that we used earlier in the course. And then multiply it by the transpose of this vector. So this vector written as a column vector. If you just multiply that, then you're going to get the column vector whose elements are the Faulhaber polynomials themselves, from the 0th one to the 7th one. And then when we want to take the linear combination that we're interested in, that really just amounts to multiplying on the left by this vector of coefficients. So this matrix product, which you can get your computer to evaluate very simply, will immediately spill out the required sum that we're interested in. So actually with a computer in hand, it's actually a very reasonably simple kind of thing to do. But I want to point out, okay, for just in a second we'll see the importance, that of all the stuff that's on here, especially all this data in this table, it turns out that actually only this number right here, okay, only that number really ends up figuring in the picture. Okay, so that's not clear at this point, but after we do the calculation, you'll be able to see why. And so this is really kind of remarkable that all this information that we need, actually most of it is unnecessary. All what we really need is this bottom entry here. And of course, once you understand that, then you can do this kind of calculation much more simply, because you can ignore everything. You know immediately what that thing is because it's just 1 over 8. So essentially no work is required. So we take those linear combinations of Faulhaber polynomials and we get a formula for our assigned area of our spline as a function or polynomial involving n. And it's 1 over 2 times n to the 8. And here is that linear combination of Faulhaber polynomials. Minus 1/3 n squared plus 11 over 12 n to the fourth minus 5 over 6 times n to the sixth plus 1/4 n to the 8. And it's the 1/4, that's happening because we had a 1/8 there, and we ended up taking 2 times that one. That was the coefficient of 2 that I pointed out a couple of times, the 2 times the s sub 7. So when we take the 2 times the 1/8 that was in that bottom right-hand corner, we get a 1/4. And then we have to divide by 2 times n to the 8. So what do we get? So let's rewrite this now with the constant term here and the powers of n in the denominator increasing here. So when we divide by n to the 8, this thing here will give us 1 over 8. And then this one here will give us minus 5 over 12 with an n squared in the denominator. Over here 11 over 24 with an n to the fourth in the denominator, and minus 1/6 with an n to the sixth in the denominator. And now we can ask, okay, this is an exact expression for the assigned area of that spline that depends on n. So it's exact. But now we can ask what happens as n gets big. Well, as n gets big, these terms with the n's in the denominators, they get small. But this thing stays where it is. So obviously, this thing is going to approach 1 over 8. And 1 over 8 is the 5 minus 3 over 2 times 5 plus 3 that our fundamental formula predicts. Now you might say, well, aren't you doing some limiting stuff here, Norman? And yes, it is a bit of a limiting argument, but it's a relatively simple limiting argument, and we can make it a little bit more precise if we want to. But we can, in fact, if we want to, avoid it altogether. Right. We can just say, forget about taking limits. Let's just look at this expression. Okay, it's an expression involving n, and we'll just disregard all the stuff that has n's in the denominator anywhere. This is just the constant term. We'll just pick out the constant term. That's effectively the same as taking the limit. So we don't have to take a limit if we don't want to. We just pick out the constant term. That gives us the 1 over 8. So what we're seeing here is that this method of taking a limit, of approximating something with splines, using our earlier technology for computing signed areas of splines, using that powerful approach of Faulhaber, giving us very detailed information about the area of the spline, and then taking some kind of limit or truncation, that recovers our fundamental formula for us. But in the process, a lot of that Faulhaber detail gets just washed away. It becomes almost irrelevant. So when we're going from the discrete Faulhaber spline kind of story to this more smooth, continuous version, we're actually simplifying things in some ways. We're kind of throwing things away. And this is why in many applications, it's sometimes easier to deal with the continuous version of things than with the discrete version. The discrete version formulas are often very detailed and have all the structure that's somehow lost when you smooth things out, and then you just get some number like all these things sort of disappear and just the 1 over 8 remains. So to finish, I would like to apply what we've learned to harvest some immediate consequences. So we've just understood the fundamental formula for this curve gamma, the curve alpha cubed alpha to the 5th. So one of the consequences that we can immediately draw is to find the signed area of a more general segment. If we go from 0 to c instead of 0 to 1. In that case, we're going to get c to the 8 over 8 because our dilation property, it's property E, tells us exactly what happens when we replace the 1 here with a c. The effect is to multiply the signed area by the factor, the sum of these exponents, so c to the 8. So it'll be c to the 8 over 8. And then if we want to generalize a little bit further and have the signed area of the segment from t to u of the same curve, that will be a difference between two such things by the additivity property. That's property B of our 5. So it'll be like the signed area from 0 to u minus the signed area from 0 to t. So it'll be u to the 8 over 8 minus t to the 8 over 8, or this quantity here. And now I want to look at what happens when we look at a portion of the curve and the area underneath it to the x-axis. Okay, so we've got the same curve, gamma there, and I've chosen 2 points on it, A and B. And we'll associate those 2 points with 2 values of the parameter alpha. So this one here will be corresponding to t, and this one will be corresponding to u. Okay, and so now let's consider the problem of finding the area underneath this segment of the curve above the x-axis. Let's call that signed area A, and it's really a signed area in this positive direction, so counterclockwise. So how do we calculate this A? Well, Leibniz already realized that there was an intimate connection between the area underneath a curve, like this, and the area subtended at the origin by that segment of the curve. Okay, and he exploited exactly this relation here. So we're following Leibniz exactly here. He realized that there were two auxiliary triangles involved. And the triangles, we can label them like this. So we'll let the point down here be C. Just project down to the x-axis and project down here to get the point D. So then there are the two triangles, OCB. That's the big triangle. Okay, so we can calculate its signed area, whatever that is. And then we can subtract the signed area of the smaller triangle, ODA. And we can also subtract the signed area of the curve gamma from T to U. In other words, that will be the signed area that when you go straight up to A, then along the curve up to B, and then straight back down to O. Okay, so what's going to remain then is this quadrilateral type region that's underneath the curve over the x-axis. Okay, so how do we calculate these various things? How do we calculate the signed area of OCB? Well, this is the point where the parameter is supposed to be u. So alpha is u. So the x-coordinate is u cubed, and the y-coordinate is u to the fifth. That means that the base times the height of this thing will be u cubed times u to the fifth, and we divide by 2. We get u to the 8 over 2. Or a better way is just to use the signed area. This is u cubed, then we're taking the cross product of u cubed with this vector here, and we get u to the 8 over 2. Similarly, for the other point, this point here with coordinate t, the signed area of this little triangle ODA will be t to the 8th over 2, and we're going to subtract that from the big one. And then we're also going to subtract the signed area determined by the segment of the curve, which is what we've just calculated up here. From t to u, the segment would be u to the 8 minus t to the 8 over 8, and so we have to subtract that. And what do we get? Well, we get this u to the 8 minus t to the 8 common factor, basically 1/2 minus 1/8, which is 3/8. And so we get 3/8 times u to the 8 minus t to the 8. And you can check that this is the same thing that you would get if you have done a traditional calculus course. If you consider the function y equals x to the 5 over 3. There we go, 5 over 3, and you add 1, you get 8 over 3. Take the reciprocal, you get 3/8, and that's going to be the same thing. So this gives the same kinds of answers to questions, but this is very simple technology because we basically just established this fundamental formula. Now we're seeing that it actually connects with a limiting approach involved in classical calculus. So we're not really steering away from traditional thinking. So now we're in a position to really approach the fundamental theorem of calculus, which is a ramping up of this fundamental formula to a bigger picture. So there's much to learn. I'm Norman Wildberger. Thanks for listening.